All right. Probability rules. So it just takes probability and takes an extra step to it. The first one, determining a sample space for multiple outcomes. That's the big thing, like I mentioned in the last module, that you are looking at like event A, event B. There's multiple things happening here. And the biggest recommendation for this is to look at it one at a time. So here a coin will be tossed 3 times. Each toss will be recorded as heads or tails. Given the sample space, describe all the possible outcomes. So the sample space is still all the possible outcomes. Man, I got to do it 3 times. So this isn't fun. Tails, tails, tails. Tails, tails, heads. Tails, heads, tails. Heads, tails, tails. Where do I want to go from here? Tails, heads, heads. I'm going to confuse myself. I know how many there should be, so. I like to do a chart. I should have done a chart instead of this. Tails, heads, heads. Heads, tails, heads. Heads, 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 tails. And heads, heads, heads. Okay. By the way, just a shortcut. I don't know if we do this, but this could be helpful. All the possible, you do 2 to the n, which n is there's 3, so 2 to the third. That tells you that there should be 8. 2 times 2 times 2, just to make sure you get them all. Okay. This is the hardest one. They don't make you do like 4, so that should be the hardest one. So the sample space is all the possible options. The event here is that the first toss is a head. So I just go through this list right here. It would be HTT. It could be HTH. It could be HHT, or it could be all H's. Okay, so where your heads is first, right? Where your head is first on those. All right, so that's not much different than the one we did the last module, but you just got to make sure you get all those different ones. What is this one? I think we mentioned the symbols briefly last class, or maybe it was 2 modules ago. We'll refresh over them real quick. All right, so this symbol right here is the union. It means or in math. And what I think about is it brings it all together. Okay? They don't really talk about this symbol, but this said that, I guess this set, you don't really need it. But just to let you know, just in case you see it. So, or is where a marble is selected from a bag containing 8 marbles numbered 1 through 8. Look at the different events. So event A is a marble selected has an even number. Event B has a number greater than 3. The way I think about this, just because, say we're both playing this game. I win if I get an even number. She wins if greater than 3, right? Okay. So if you want to write those out right here, my sample space for A would be 2, 4, 6, 8. Greater than 3 would be 4, 5, 6, 7, and 8. Okay. The or brings them together. I want me or her to win. So I don't care which one of us wins. I just want one of us to win. So I get greater than 3 is 2, 4, 5, 6, 7, or 8. As long as we get one of those numbers, one of us will win, right? Okay, so we're good. That just brings them together. The other symbol here is the upside down. Again, they don't talk about the symbol here, but just in case you see it, that means and it's what we share. This time I want both of us to win, okay? So what numbers allow both of us to win? It would be 2 only allows me to win. A 4, a 6, and an 8. If we get a 4, 6, or 8, we both win, okay? So it's what they share. And then the complement of A. The complement would be what is not in A. So if A is even numbers, the complement would be odd numbers. All right? That makes that easy with the even and odd. Use a Venn diagram. All right. Find the probabilities of each. Okay. So the Venn diagram below shows the 13 students in Mr. Wong's class. The diagram shows memberships of computer club or math club. All right. So the probability of A is the computer club. So if I was doing the probability of the computer club, I have this one, this one, this one, this one, and this one, and this one, right? There are 6 out of the 13 students. For B denotes the students in the math club. 1, 2, 3, 4, 5. I still count these, right? 6, 7, 8. So those are in the Venn diagram. It's okay that they overlap. All right, the word or, this is where it comes in handy. The word or right here is the union. It brings together. The way I think about it with Venn diagram is it's everything inside the circles. Okay. So it is these 3 right here, right? Or no, it's all of them. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So as long as they're in either of the circles or both, okay? If I ask Lucy if they're in computer or math, just because they're in both, they'd still say yes. Okay. And, the word and, the word we associate with that is the intersection. The reason they do that is because that is the overlap of the circles. So that is where the circles intersect, okay? So Lucy, Sam, and Greg would be 3 out of 13. All right, so now it kind of gives me a formula. I try not to do a bunch of formulas when we are in probability because I think it gets complicated or can get real complicated. But we should be able to do this one since we have all the information. So 6 out of 13 is A, plus 8 out of 13 is B, minus A and B is 3 out of 13. Okay? So to add fractions, you just do 6 plus 8 minus 3. That would be 11 out of 13. Well, if we notice right here, this is the same as this, right? So that's what this problem says, and that is a formula right here. To find A or B, we can add up A plus B minus A and B. Okay, I don't like formulas, so let's think about this for a second. If I ask what is in A or B, and you just add them up, I get 6 plus 8 is 14, right? Just think common, don't think formulas here. I know we kind of did this problem, but just think in common sense right here. If I have 6 people in A and 8 people in B, and I add them up and I get 14, I think I'd have 14 out of 13. Probability doesn't even make sense, right? Because you can't have more than 100% in probability. What is wrong with just adding 6 and 8? Like, what common sense-wise did I do that messed it up? If I add these 6 people for A, and then I add these 8 people for B, why can't I just add those up and get my answer? Because a lot of times in the word or means add in math. What's wrong when I add those together?
You're adding the same person twice.
I added this group of people twice, okay? So that is why you subtract this out. So you can add up A, you add up B, and then subtract this one, and it gives you the answer. So what you want to think about here is you want to add them up and then subtract anything that you added twice. That's kind of the idea behind this. So this is probably the hardest rule that they have in the probability is the addition rule. So let's move on to the table one. All All right, so we got dessert or no dessert and lunch or dinner. Do people eat dessert more at lunch or dinner kind of table here? First of all, it starts easy. What is the probability that a customer came for lunch? All right, so first thing we always want to identify because it makes it easy. That's my total amount right there, right? Okay, so the probability that they came for lunch. So lunch would be the total of these. If I add these up, 23 plus 54 would be 77, right? I'm going to go ahead and add up all these real quick. 61, 63, and my total, those both numbers should add up to be 124. So if I have 63 plus 61 is 124, 77 plus 47 is 124. It's always nice to have those numbers. It makes it work faster. Okay. So what's the probability that the customer came for lunch? So lunch would be 77 out of 124. All right. What's the probability that a customer came for lunch or ordered dessert? So came for lunch would be this number, right? Or ordered dessert would be this number, 77 plus 63. What is wrong with that number right there?
Bigger than your total?
What? It's bigger than my total. Why is it bigger than my total? If I add up the people that had lunch, I get 77. If I add up the people that had dessert, I get 63. So if I add up 77 and 63, what's wrong?
Too big.
What?
It's too large.
It's too large. Why is it too large? What'd you say a second ago?
You got it.
Didn't I add this number right here twice? Because I added it when I did the lunch row, and then I added it when I did the dessert column. So I need to subtract that out of that. So 77 plus 63 minus 23 is 117. So 117 out of 124. Does that make sense? Technically, when you're in a chart like this, you could add this and this and this and do it that way. But mathematically what you're doing is you add the lunch, you add the dessert, but I added that number twice. So I got to take it out. All right, since y'all didn't get that fast, I got to do another one. This is a good one, though. It's still lunch and dessert. Didn't get a new topic, but I got what I was looking for here. It's the same numbers as we had before, too. 100, no, it's not the same numbers, I guess. 124. All right, so first of all, I'm going to fill out my chart, add these up. 77, 61, 63. It is the same numbers. 124, okay. What's the probability that a customer came and did lunch and dessert? Lunch and dessert is just this number right here. The and is just lunch and dessert, 23 out of 124. All right, now the probability that it's or, I add up the lunch, I add up the dessert, and since this is the same numbers that we just had, that's not very fun, but so 77 plus 63, but I added that 23 twice, so 117 out of 124. Okay, that's the difference between and or. You got to be careful with those. We did that one last time. Conditional, conditional, conditional. Maybe I will save. Let me look real quick, and I can save. Maybe I'll save that for the next. Come on. Yeah, there's only 1, 2, 3, 4, 5, 6, 7. That'll give us 13 topics to do on Tuesday. I think those will go fast though.